Noche Cósmica.
Somewhere in the outer reaches of our solar system, suspended in darkness beyond the orbit of Jupiter, there exists a world so shrouded in mystery that we have only recently begun to understand what lies beneath its veil. Imagine descending through layers of fog so thick that it swallows light itself, orange and amber haze that never quite parts, never quite lets you see all the way to the ground. This is Titan, Saturn's largest moon, and the question that has haunted astronomers for centuries is simple but profound. What secrets does that impenetrable orange veil conceal? If you find yourself drawn to slow, unhurried journeys through the cosmos, stories that unfold at the pace of discovery itself, I'd invite you to subscribe to this channel, where we'll return again and again to explore Titan's calm mysteries, episode after episode, letting each new fact settle gently into the landscape of what we've already learned. Now, let yourself imagine what it might feel like to sink downward through that haze. Picture, if you will, a descent that takes not minutes but hours. The air around you thickens with each moment. What begins as a faint amber tint gradually deepens into something richer, more substantial, a nitrogen atmosphere so dense that the pressure at Titan's surface rivals that of Earth's own ocean depths. There is a weight to this world, a heaviness that wraps around everything, softening edges, muffling sound before it can fully form. The nitrogen fog is not still. Occasionally, perhaps once in a Titan day, which lasts more than 2 Earth weeks, the clouds part ever so slightly, and when they do, something remarkable begins to fall. It comes not as rain, not as you might know it on Earth, but as a gentle patter of liquid droplets, methane and ethane mixed with trace compounds, descending slowly through that thick atmosphere. The sound, if there were ears to hear it in that place, would be almost imperceptibly soft, a whisper rather than a drumming, each droplet taking its time to reach the ground below, slowing as it falls through the denser air near the surface. This is precipitation on an alien world, yet there is something oddly familiar about it. It falls as rain falls anywhere, drawn downward by gravity's patient insistence, feeding a landscape that has waited in silence for billions of years. What makes this haze so extraordinary is not merely its thickness, but its composition, its very identity. It is primarily nitrogen, the same element that makes up 4/5 of the air you breathe on Earth. Yet here on Titan, nitrogen becomes something else entirely. It becomes a medium, a canvas, a thick cushion that separates the cold sky from the cold ground. Mixed within this nitrogen are methane molecules and trace amounts of other hydrocarbons so complex they give the entire moon an orange cast when viewed from space. These compounds form what scientists call tholins, organic molecules that rain down constantly as a kind of chemical snow, accumulating over eons, enriching Titan's surface with the building blocks of greater complexity. Within this haze, there is a profound quietness, not the silence of vacuum. Titan's atmosphere is thick enough to conduct sound, but rather a muffled, absorbed silence, the kind you might hear in a very old forest after snow has fallen, or deep underwater where sound travels but seems distant, dreamlike. The clouds here never fully scatter. The sun, when visible at all, appears not as a bright point, but as a diffuse, warm glow, as though the entire sky itself were softly luminous. Day and night blur into one another. There is no harsh transition, no sudden darkness or sudden light. Instead, there is an eternal amber twilight, a perpetual dusk that lasts and lasts, unchanging except for the slowest of variations as Titan moves in its orbit around Saturn. The wind moves through this haze with purpose, but without haste. On Titan, the wind does not howl or rush. It flows with a patient dignity, shaped by vast atmospheric circulation patterns, by the tilt of Titan's orbit, by the distant gravity of Saturn itself. The wind shapes the landscape below. This we would eventually learn, carving dunes of hydrocarbon sand into patterns as subtle and as timeless as the ripples in a desert that has never known rain except for these rare methane downpours. The wind is a sculptor here, but it works slowly, across timescales that dwarf human patience. One might ask, how can a world so cold, so distant, so utterly alien offer us anything like tranquility? Yet there is something profoundly calming about Titan's very remoteness, its utter separation from the harsh radiation and violent variability of the inner solar system. Here, at Saturn's side, more than 1 billion kilometers from Earth, there is a kind of geological peace. Change happens, yes, but change happens at a tempo almost beyond human comprehension. A dune that took 10 million years to form will stand largely undisturbed for another 10 million. A methane lake once established persists in its stillness for epochs. The very slowness of Titan's processes, its thin winds, its infrequent rains, its cold that makes chemistry move at a funeral pace, creates an unexpected serenity. The orange haze that wraps Titan is not a barrier to wonder then, but an introduction to it. It is the threshold that guards the mysteries below, the first sensation you would encounter if you descended into this distant world. It is thick and soft and patient, and it whispers of a realm fundamentally different from our own, yet governed by the same laws of physics and chemistry that govern everything in the universe. Beneath that haze, as we will discover, lies a landscape of extraordinary strangeness and unexpected beauty. But first, we must sit with this image, a world shrouded in fog, breathing gently, waiting in its amber silence for the next visitor to finally arrive and learn its secrets. There is something profoundly calming about studying a world that asks more questions than it answers. Titan, in its perpetual amber stillness, offers us precisely that gift, a place so distant and so wrapped in mystery that simply turning our attention toward it becomes an act of patience itself. And there are layers within Titan's haze, secrets waiting in those methane seas and beneath that ancient icy crust, that deserve to be explored, not in a single breath, but across many slow, careful evenings. If you find yourself drawn to these distant, unhurried journeys through our solar system, to the kind of science that unfolds like a story told in the dark, where each new discovery leads gently toward the next question rather than rushing toward answers, this channel exists precisely for you. We return, again and again, to places like Titan, lingering longer each time, letting the details accumulate like sediment in still water. Each episode builds on the calm foundation of the last, creating a landscape of knowledge that rewards patient attention. Consider subscribing to follow these slow, science-rich explorations of our neighboring worlds. In the episodes to come, we will descend deeper into Titan's atmosphere, watching how those orange hazes scatter and refract the distant sunlight. We will trace the shorelines of its methane seas with the kind of attention usually reserved for beloved landscapes. We will contemplate what might live or persist in those cold lakes, and what the subsurface ocean beneath Titan's crust might yet reveal about chemistry and the possibility of life in forms we have yet to imagine. We will sit with the scientists who have studied this world for decades, patient watchers of a single moon's unfolding mystery. When you subscribe, you are not simply bookmarking a channel. You are making a commitment to slowness, to the understanding that some truths about our cosmos cannot be rushed, that wonder deepens with time, and that the most profound knowledge often arrives wrapped in layers of gentle questioning rather than certainty. Titan rewards this approach, this willingness to return again and again to its haze, its seas, its ancient winds. The story of Titan does not end in a single telling. It accumulates across seasons, across missions both past and future, across the careful observations of astronomers and planetary scientists who have made this world their life's work. There are details we have yet to share about how Cassini mapped those frozen canyons and traced the outlines of those impossible lakes. There are future instruments being built right now in laboratories around the world, destined to descend through that nitrogen fog and touch down on Titan's surface, to whisper back their discoveries across the vast distance that separates us. Each journey we take here is part of a longer conversation with the cosmos, a conversation that began the moment Christian Huygens pointed his telescope towards Saturn and saw a point of light that moved, and realized that point of light was a world. That conversation continues now. In the centuries between that first glimpse and our current moment of knowing, countless observers and thinkers have added their voices, their curiosity, their patient attention, and Titan itself, spinning in its slow dance around Saturn, has waited. It waits still, patient as only a world billions of miles away can be. So if these gentle journeys speak to something in you, if you find yourself calmed by the prospect of exploring worlds at their own pace, of letting cosmic knowledge unfold in whispered layers rather than sudden shocks, subscribe now. Join us as we return to Titan's haze again and again, each time moving deeper, asking quieter questions, discovering that the most profound relaxation often comes from contemplating the slow, steady mysteries of distant places that we may never see with our own eyes, but can know through the patient gathering of evidence, through the stories told by those who have devoted their lives to listening to what these worlds have to tell us. The adventure you are beginning is measured not in hours or even years, but in the kind of deep time that makes the solar system feel intimate. And we will meet you there, at each corner of that unhurried exploration, time and again. The story of Titan truly begins not with grand revelation, but with the quiet click of a telescope lens on a winter night in 1655, when a Dutch astronomer named Christian Huygens turned his handmade instrument toward the pale, distant disk of Saturn. What he saw that night was so subtle that it might have escaped notice entirely. A small point of light, moving steadily beside Saturn through the long hours of observation, keeping time with the planet's own slow rotation. Not a star, something tethered, something orbiting. Huygens understood immediately what he had found: a moon, Saturn's first moon. He named it Titan, drawing the name from classical mythology, where the Titans were ancient giants who walked the cosmos before the Olympian gods. The name carried a weight of significance that, looking back across the centuries, seems almost prophetic. What Huygens could not possibly have known was that this distant moving point of light represented one of the most complex, strange, and profoundly calm worlds in our entire solar system. In those early years after the discovery, Titan remained what it would be for the next 3 centuries, a nearly featureless point of orange or pale yellow light in even the most powerful telescopes. Astronomers could track its motion with increasing precision. They could calculate its distance from Saturn, measure its orbital period, about 16 days, and confirm that it moved in a near-perfect circle. But the world itself remained veiled, utterly hidden. The telescope brought Titan no closer to human understanding, even as it made the world's existence undeniable. What a strange kind of knowledge that must have been, to know something exists, to have measured its properties, and yet to be entirely ignorant of its nature. The centuries unfolded slowly. Newton's physics arrived and made the orbits predictable. Better telescopes were built, larger and more refined, yet Titan stubbornly refused to reveal its surface. The telescope would show no clouds, no marks, no distinguishing features of any kind. It remained essentially featureless, a uniform sphere of pale orange or yellow, depending on the light and the observer's eye. This emptiness was not boring, it was intriguing. It was a question posed by the cosmos itself. What hides beneath that apparently smooth face? By the 19th century, astronomers had begun to speculate more seriously about Titan's nature. The observations accumulated. The moon was relatively large for a satellite, perhaps 4,000 or 5,000 kilometers across, though the measurements were uncertain and would remain so for centuries. It orbited at a considerable distance from Saturn, beyond several other moons. And there was something in the way light reflected from Titan's surface that suggested it might not be made of bare rock at all. Could it be covered in ice? Could it have an atmosphere? These questions lived in the realm of patient speculation. No astronomer could answer them with certainty from Earth. Titan existed as a scientific mystery, a world about which everything worth knowing remained unknown. And in that ignorance, it gathered a strange kind of glamour. Each observer who turned a telescope toward Saturn in the evening sky and found Titan faithfully moving through its orbit was touching, in a small way, the boundary of the known universe. Here was a world no human eye would ever see clearly, no human voice would ever reach. It was utterly inaccessible, utterly other, and yet it was real, measurable, trackable, knowable in the abstract if not in fact. The patience required to study such a distant world, even passively, cultivates a particular kind of contemplation. An astronomer observing Titan in the 19th century, knowing that nothing visible had changed since Christian Huygens first saw it 300 years before, might feel something like what we might call cosmic patience, the sense that understanding sometimes unfolds not in moments of dramatic revelation, but in the slow accumulation of observations across generations. Each passing century brought no closer view of Titan's actual surface, no closer understanding of what lay beneath that pale orange sphere. Yet each century also brought more refined measurements, better telescopes, a deeper sense of certainty that something genuinely interesting existed there, waiting. This long period of patient ignorance, of knowing without understanding, might seem frustrating to us now, living in an age of rapid technological change and instant information. But there is something deeply peaceful about it too. The mystery of Titan was not urgent. It could wait. It could be wondered about in quiet moments at the telescope. It could inspire philosophical reflection on the nature of distant worlds and our place among them. The moon orbited on, indifferent and calm, turning its mysteries over and over, visible to those who knew where to look, but yielding nothing of its secrets. The centuries that followed Huygens's glimpse were patient ones. Astronomers pointed their telescopes at that pale orange disk again and again, generation after generation, watching it move in its silent orbit around Saturn, a faithful companion locked in an ancient gravitational dance. Yet for hundreds of years, Titan remained essentially unknowable, a smooth, featureless sphere of mysterious hue, obstinate in its refusal to reveal anything of its nature. What was it made of? Did it possess an atmosphere at all? Or was it simply a cold, barren rock, its color derived from some exotic surface material that light reflected from in those particular wavelengths? By the turn of the 20th century, astronomy had begun its transformation into something far more precise. The telescope alone, patient as it was, could no longer answer the deepest questions. A new tool had arrived, spectroscopy, the art of breaking light into its component colors, each one carrying a whisper of information about the distant world from which it came. When sunlight bounced from Titan and made its long journey back to Earth, that light carried chemical signatures written in invisible ink. An astronomer with a spectroscope could decode those signatures. Each element, each molecule, absorbed and emitted light at specific wavelengths. It was like listening to a unique song that only one substance could sing. And so the careful watching began. Astronomers positioned their instruments, spread that tangerine light across their prisms and diffraction gratings, and began the patient work of reading Titan's spectrum. The suspense, if we can call it that in the context of something so slow and methodical, was genuine. Would this distant moon prove to be a dead cinder, or might something unexpected live in its light? The breakthrough came gradually, building across observations from multiple observatories through the 1940s and into the 1950s. There, in the spectrum of light reflected from Titan, appeared lines of darkness, where light had been absorbed, absorption lines that corresponded to methane, that simple molecule of carbon and hydrogen, CH4, methane on Titan. The realization settled slowly into the astronomical community, like snow falling in an already cold landscape. Titan was not a bare rock. It possessed an atmosphere. A gaseous envelope surrounded this world, and that atmosphere contained methane, the same hydrocarbon that rose from swamps and cattle pastures on Earth. Here it was, out there in the cold distances, around a moon that orbited a ringed planet, millions of miles away. What did it mean for an object so far from the sun to possess such an atmosphere? The question hung in the minds of scientists. Methane is volatile. It evaporates easily in warmth. For it to exist as a gas around Titan meant that Titan must be extraordinarily cold. And yet, cold as it might be, cold enough that methane survived as gas rather than freezing into ice, the moon retained this invisible mantle around itself. There was something paradoxically gentle about the image this created. Here was a world wrapped not in granite or silicon, but in a blanket of organic molecules, ancient chemical compounds that had never seen the light of a star quite so distant. Throughout the mid-20th century, as observations accumulated, the picture grew more intricate. Spectroscopic analysis suggested that Titan's atmosphere was not merely a thin trace, but something substantial, perhaps as thick as Earth's own atmosphere, perhaps even thicker. How could such a small moon, so far from the warmth of the sun, maintain so much gas? The puzzle deepened with each new measurement. And all the while, beneath that visible orange haze, beneath the methane that revealed itself to patient spectroscopy, what else might be hidden? What lay beneath the clouds that the telescopes could not penetrate? On Earth, nitrogen and oxygen comprise nearly all the air we breathe. Titan, it seemed, was different. Its air was alien, nitrogen-rich but laced with methane, exotic by our standards. And where there was methane in cold conditions, there might be something more. The spectroscope suggested hints of other hydrocarbons, other organic molecules. A world of chemistry, all of it unfolding at temperatures that would freeze carbon dioxide solid. There was a quality of patient revelation in these discoveries, a sense that Titan was slowly, reluctantly, allowing itself to be known through the patient application of human ingenuity. No spacecraft had yet ventured to that distant moon. No instrument had touched its surface or drawn samples from its atmosphere. Yet piece by piece, photon by photon, the light that Titan reflected was teaching us about itself. And what it taught us was that this was no simple frozen cinder. This was a world with chemistry, with dynamics, with an atmosphere that spoke of complexity. The methane lines in the spectrum, those dark marks against the rainbow of light, had opened a door that would never close. Behind that door lay mysteries that would take another 50 years and the arrival of actual spacecraft to begin to illuminate. And then, on November 12th of 1980, after a journey of more than 4 billion kilometers through the silence of space, the Voyager 1 spacecraft drew close enough to Saturn to finally, truly see its largest moon. The solar panels, which had been drinking in the distant sun's faint warmth for nearly 4 years, tilted slightly to orient the cameras. The star field beyond grew steadily brighter, and there, in the viewfinders of instruments that had traveled farther from Earth than any human creation before or since, Titan appeared at last, not as the distant point of light that astronomers had studied through telescopes for 3 centuries, but as a disk, a sphere, a world. What they saw was utterly, profoundly still, a perfect circle of burnished orange. No mountains, no valleys, no craters, no details whatsoever except the faintest suggestion of shading, as if someone had painted a smooth sphere with a single, patient brushstroke of peach and amber, then set it down to dry. The Voyager cameras, which had peered through the turbulent clouds of Venus and captured the roiling great red spot of Jupiter with exquisite clarity, found only an impenetrable veil, a uniform, seamless haze that seemed to absorb every detail beneath it, as if Titan were wrapped in a blanket, drawn entirely closed against the universe's gaze. There was, for many who had waited so long to see this moment, a peculiar kind of quiet letdown woven into the wonder. How strange to journey so far and discover only mystery. The scientists gathered in laboratories, and mission control centers recognized instantly what Voyager's images suggested, that Titan possessed not merely an atmosphere, but a dense one, possibly the densest atmosphere of any moon in the solar system. The methane that spectroscopy had hinted at years earlier seemed to be organized into layers, into organized clouds and haze structures so thick that visible light could not penetrate to the surface below. Titan was hiding. That was the real discovery. But there was something almost gentle in that disappointment, something that would prove to ripple outward through decades to come, because the more you cannot see, the more the mind fills the emptiness with possibility. The universe abhors a blank canvas less than the human imagination does. Beneath that smooth orange veil, there might be anything, anything at all. Canyons, vast plains, seas, mountains of ice so tall they scraped against the upper atmosphere, or something stranger still, something so alien that no one yet living had conceived of it. The very featurelessness of Titan, paradoxically, became its greatest invitation. In the months and years that followed the Voyager encounter, that orange sphere haunted the scientific imagination in a way that a detailed photograph might never have done. Titan became the problem that would not sleep. Why was it so hazy? Why could we not see through? What chemistry was occurring up there in that nitrogen-methane atmosphere, in those high clouds that caught the sun and bent its light into that warm, peaceful, utterly obscuring glow? The absence of information became a presence all its own, a gentle pressure, a soft urgency, a certainty growing in the backs of minds that Titan would have to be visited again, someday, with better instruments, with patience enough to wait, with cameras that could see through the haze itself, or instruments that could feel their way through it using radar, using infrared, using whatever means necessary to reveal what the golden veil had so carefully concealed. Voyager 1 had delivered something unexpected and precious. Even in its failure to deliver a clear image, it had delivered a question, and questions, unlike answers, have a way of deepening over time. They gather weight, they grow roots, they wait. And so began, quietly and without fanfare, the long interval of wondering. 24 years would pass before another spacecraft would arrive at Titan's orbit. 24 years of speculation, of modeling, of nighttime conversations in university offices, where scientists would sketch out theories on whiteboards, imagining landscapes that no human eye had seen. Was there liquid on the surface? Could there be? The models suggested yes, that if methane rained from those clouds, it would gather in the low places, forming oceans not of water, but of something stranger, something cold and hydrocarbon-rich. But these were whispers, educated guesses, beautiful imaginings. That smooth orange sphere, then, was not an ending, it was an opening, a door left deliberately, mysteriously ajar, and in the hush of that patient darkness, in the silence between Voyager's brief kiss and whatever would come next, the The real relationship between Earth and Titan could finally begin. Not the relationship of seeing, but of wondering, of longing, of patient, determined curiosity that refused to let the question go. And so the world waited. 25 years stretched between that first orange glimpse in 1980 and the arrival of a new messenger. It was a peculiar kind of patience that settled over the astronomical community. Not idleness, but a slow, methodical turning of minds toward a world they could not yet see clearly. Voyager had left them with questions wrapped in mystery, and those questions would occupy an entire generation of planetary scientists in a way that perhaps only the truly unknowable can. During those decades, a quiet scholarly work unfolded in universities and research centers scattered across the planet. Without new images, without fresh data from the surface, scientists constructed Titan in their minds. They built it from fragments, from the faint spectral lines that revealed methane, from theoretical models run on computers that grew faster and more sophisticated with each passing year, from analogies drawn to Earth and to Venus, from educated guesses about what such a distant, shrouded world might harbor beneath its veil. It was detective work of the gentlest kind, a slow accretion of thought. Radiative transfer models were crafted to understand how light moved through Titan's thick atmosphere, how the haze particles scattered and absorbed the distant light of the sun. Scientists calculated what the surface temperature might be, ran simulations of atmospheric chemistry, imagined how the wind might move across terrain they could not see. Some wondered whether the surface might be entirely smooth, a global ocean of liquid hydrocarbons perhaps, or a vast plain of ice as hard as rock in that bitter cold. Others speculated that mountains might rise, that canyons might wind through the darkness below the orange clouds. The truth was, no one truly knew. There was something meditative about this period of not knowing, about working with the fragments that remained. In those quiet hours, in laboratories where the hum of computers and the soft scratch of pen on paper were the only sounds, planetary scientists became something like archaeologists of a world no human had touched. They examined every clue with a kind of reverent attention. The composition of Titan's atmosphere, nitrogen, methane, trace amounts of other organic compounds, suggested a chemistry far more complex than the simple nitrogen-oxygen mix that surrounds Earth. What might that mean for what lay below? Papers were published, conferences were held, models were refined. Each new observation from telescopes, each careful measurement of Titan's thermal properties, each theoretical prediction about how such a world might have formed and evolved, added another thread to the growing tapestry of understanding. The work was slow, incremental, almost imperceptible from one year to the next, yet it accumulated, it deepened. Scientists studied the chemistry of Saturn's upper atmosphere, looking for hints about what might have rained down onto Titan over billions of years. They considered the processes that had shaped the moons of Jupiter, drawing parallels and finding differences. They thought about tidal heating, about the energy that might slosh through Titan's interior from Saturn's powerful gravitational pull. Could there be warmth there, hidden in the cold? Could there be places where rock and water and energy combined in ways that might kindle something approaching life, or at least the slow build-up of chemistry that life might someday depend upon? The waiting had its own rhythm. A season would pass. A new paper would emerge from the archives of astronomical literature. Another theoretical refinement would be added to the model. Young graduate students would begin their research careers studying Titan, working with what was known and what was imagined, building hypotheses that would only be tested decades hence. This was part of the profound patience that planetary science demands. The willingness to ask questions about worlds you might never see in your lifetime, to contribute to understanding that will be completed only by future generations. And yet, underneath this scholarly calm, there was something else. There was anticipation. There was a collective knowledge, held quietly and with certainty by the planetary science community, that a new spacecraft was being built, Cassini. It would be large, sophisticated, ambitious. It would not merely fly by Titan on a brief encounter. It would enter Saturn's orbit and make repeated visits to that mysterious moon. And more than that, it carried a probe, a lander, something that would actually descend through that opaque atmosphere and touch the surface. For the first time in human history, something made on Earth would land on this distant, cold, methane-soaked world. But that day was still years away. The spacecraft was being assembled, its instruments carefully crafted, its trajectory calculated. Throughout the 1990s, the anticipation deepened in its own gentle way. Scientists refined their models further, considering what instruments the Cassini mission might reveal, what they most hoped to learn, what mysteries they most wanted to solve. The waiting became a kind of meditation, a slow, patient preparation for the moment when Titan would finally step out of the haze of imagination and speculation and become real again, known, touchable through the extended sense of human technology. There was beauty in this uncertainty, in this long pause between knowing and not knowing. Titan existed in a state of profound possibility. It could be one thing or another, or something that no one had yet imagined. The surface could be smooth or fractured, young or ancient, simple or bewilderingly complex. The chemistry could be dull or fascinating, familiar or entirely alien. For those patient enough to wait, for those willing to sit with questions unanswered, Titan remained a world of infinite potential, a world that existed as much in the realm of imagination as it did in physical reality, orbiting Saturn in the darkness, keeping its secrets close. For 7 years, Cassini traveled through the cold dark of the solar system, a spacecraft so heavy it could barely move on its own, so laden with instruments and fuel that it had to be the size of a small house just to carry everything humanity wanted to ask of Saturn's realm. And then, in the summer of 2004, it arrived, not with fanfare or sudden urgency, but with a quiet gravitational surrender, as the enormous mass of Saturn gently caught hold of this visitor and began to fold it into orbit. The engines fired in a long, carefully calculated burn, and Cassini became Saturn's moon, a moon that would move and watch and measure for more than a decade to come. What made this arrival particularly profound was that no spacecraft had ever attempted what Cassini was about to do. Voyager had been a messenger, a swift flyby that opened a single brilliant window and then closed it forever. But Cassini was a dancer, meant to waltz slowly around Saturn and its moons in an unhurried spiral, passing close and far, gathering data in a rhythm that would take not days, but years to fully play out. The spacecraft's orbit was designed with such precision that it would thread between the orbits of Saturn's moons, moving among them like a careful visitor learning the geography of a new home, one encounter at a time. During those early months of 2004 and into 2005, Cassini performed what is called the Saturn Orbit Insertion Sequence, a series of gentle orbits that gradually brought it closer and closer to the planet, and closer still to the mysterious, haze-wrapped world of Titan. The spacecraft would drift past Titan once, then circle back, gaining proximity with each pass. The scientists and engineers on Earth watched these trajectories with a peculiar kind of patience, the patience of people who have already waited so long that a few more weeks seemed small. They knew what was coming. They could see it in the calculations. And they waited, and they watched, and they let the mathematics of gravitational mechanics carry Cassini inexorably toward the moment that would define this entire mission. Somewhere during this slow approach, a strange anticipation began to build, though it was not the frantic kind. It was quieter than that. It was the feeling that comes when you have prepared for something so thoroughly, for so long, that you have begun to understand it in your bones. The Huygens probe was attached to Cassini's side like a small child clinging to a parent. And everyone who had worked on that probe, the engineers, the scientists, the people who had spent years thinking about atmospheric chemistry and parachute dynamics and data transmission across the void, they all knew that soon, very soon, Huygens would be released. It would be fired toward Titan like an arrow, a small arrow aimed at a world that no one had ever touched, and it would have to survive not only the approach but the entry, the descent, and the landing. No one had ever landed on Titan. No one had ever tried. The magnitude of this fact hung in the background of every decision, every orbital adjustment, every course correction that Cassini made. When you send a probe to land somewhere, the landing itself is only the culmination of countless moments that came before it, countless moments of preparation, of calculation, of hope, rendered into mathematics and fuel, and carefully arranged silicon and metal. Cassini's slow, unhurried orbits around Saturn during those early months were all part of this larger act, a kind of gentle preamble to a story that was already written but had not yet been read aloud. The temperatures in space around Saturn are incomprehensibly cold. The distance from the Sun has rendered it so far in the periphery of our solar system that the Sun itself appears as merely a bright star, no more significant to Titan than any other star in the night sky. And yet Cassini, a machine built by human hands, carried on board the warmth of human intention, of human curiosity, of the desire to know what lies beneath that orange veil. The spacecraft's instruments were already beginning their careful observations, their gentle sensing of Titan's atmosphere, their measuring of the magnetic fields and radiation around Saturn's orbit. But the probe, the small one that would actually descend and touch the surface, waited in silence, attached to its mother ship, patient as only machines can be patient. In those months and years between Cassini's arrival and the eventual descent of Huygens, there was a peculiar kind of meditation happening among those who followed these events. How does one describe landing on a world that may never have felt the touch of anything from the outside? How does one imagine what it will be like to have instruments taste the air, to have a camera open its eye for the first time on a surface that has existed for billions of years without observation? The scientists gathered the data from Cassini's early flybys, began to build their models more complete, began to refine their understanding of what awaited below. They studied the spectra, the density, the winds, the composition. They prepared themselves not with anxiety, but with the quiet focus of people who understand that they are about to witness something profound. Each orbit that Cassini completed brought it closer to the moment when Huygens would be released. Each measurement, each image, each data point fed into the larger understanding, the larger preparation. The spacecraft moved through Saturn's system with the grace of something that has been given all the time it needs and all the fuel it requires. There was no rushing, no urgency beyond the urgency of purpose itself. This was how we explored distant worlds, not with speed, but with patience, not with certainty, but with careful, meticulous care. Cassini had arrived at Saturn, and in arriving, had brought with it the possibility of finally, truly knowing what Titan concealed beneath its perpetual haze. On the morning of January 14, 2005, a small spacecraft named Huygens, no larger than a washing machine really, began its gentle descent through Titan's dense and patient atmosphere. It had traveled for 7 years aboard Cassini, cradled in the arms of a much larger probe, waiting through the long quietude of interplanetary space. Now, at last, it separated. The release was quiet. There was no sound to mark it, no roar, no drama, only the cold mathematics of orbital mechanics, of trajectories calculated with such precision that the small probe would fall exactly where the scientists had intended, across the vast distance of 1 billion kilometers. The parachutes unfurled in silence. Think of that for a moment. There are parachutes descending through an alien sky, and no one is there to hear them open. The main chute, a 3-meter-wide umbrella of woven Kevlar and nylon, bloomed against the orange haze like a flower opening in time-lapse, catching the thin upper winds of nitrogen and methane. There was no sound of ripping fabric, no crack or snap of deployment, just the slow, patient way that a thin atmosphere resists a falling object, the way air molecules, scattered and cold and ancient, began to embrace this tiny messenger from Earth. The batteries hummed. Inside the Huygens probe, 8 alkaline batteries, the kind you might find in a flashlight or a child's toy, awakened to their purpose. They had been dormant for the entire voyage, kept in suspension, their precious electrical energy preserved for these final hours. Now they began to discharge, powering the instruments that would bear witness to what no human sense had ever perceived. The probe's onboard timer counted down. Temperature sensors stood ready. Atmospheric sensors opened their metaphorical eyes. Microphones, yes, microphones, extended into the turbulent fluid through which the probe was falling, waiting to translate vibrations into sound. The descent took more than 2 hours. Let that sink into your awareness. 2 hours of slow, gradual fall. Most of us experience parachute descents as brief, almost abrupt arrivals. We think of a few minutes of drifting, but Huygens fell and fell, slowing as it dropped, the density of Titan's nitrogen increasing with every kilometer of descent, turning that sparse upper atmosphere into something more substantial. The probe descended at a pace of roughly 4 meters per second, a human walking speed, almost. One could imagine, if one wanted to torture oneself with precision, counting off the long seconds as Titan came closer and closer. And during those 2 hours, something extraordinary happened that we did not expect to happen until after landing. The probe's infrared spectrometer, an instrument designed to measure the chemical composition of Titan's atmosphere, began to detect the surface beneath the clouds. The orange haze, thick as it was, grew slightly more transparent at wavelengths the human eye cannot see. The probe could see through it. The instruments could sense the contours of what lay below, a landscape hidden from us until that moment, a topography that had been sketched in computer models and educated guesses, now becoming real data, becoming measurement, becoming knowledge. The temperature dropped as the probe sank deeper. 60 kilometers above the surface, it was minus 130 degrees Celsius. That is so cold that methane becomes a liquid, so cold that many compounds we know as gases on Earth exist here in states we associate with solids and liquids. And still the probe fell, and still no sound marked its passage, except for the quiet electrical hum of machines doing their appointed work. Then came something genuinely unprecedented. The microphones, 3 of them, positioned on the underside of the probe, began to record. They were designed, primarily, to capture the sounds of the landing itself, the vibrations and impacts that would accompany impact with Titan's surface. But as the probe fell through the lower troposphere, those microphones picked up something that had never been heard before by human ears, the sound of wind on another world. Not a roaring wind, not the dramatic keening one might imagine from stories of alien storms. Instead, a soft susurration, a gentle whooshing, the sound of nitrogen and methane molecules slipping past the probe's heat shield, the sound of an atmosphere resisting an object's fall. It is a delicate sound, not threatening, almost intimate, the way wind sounds when you are alone in a quiet place on Earth, on a calm evening, listening to air move through distant branches. There is nothing in it of violence or drama. Instead, there is something almost like companionship, the sound of a world acknowledging the arrival of a visitor. The probe's computers processed all of this in real time, storing the data on a small flash memory module with roughly the storage capacity of a smartphone from several years later. Every data point, every recording, every measurement was encoded and formatted for transmission back to Cassini, which would pass overhead in a brief window, just 40 minutes, to catch the signal and relay it across the solar system to Earth. This was the thin margin upon which success depended. Cassini would pass above Titan as Huygens descended, and in that narrow window, the data had to be transmitted. If Cassini missed it, if the timing was off by even a few seconds, if the relay antenna on Cassini was not precisely aligned, then everything, 2 hours of descent, decades of planning, the entire history of this mission, might have been lost forever. It would have fallen into Titan's haze and been forgotten, and we would never have heard those wind sounds, or seen those first images, or measured that first breath of the Titan atmosphere in situ. But the timing held, the trajectory held, the ancient simplicity of orbital mechanics, proven across centuries of astronomy, held true once again. As the probe dropped lower, it entered the realm of the clouds themselves. Below 10 kilometers, Titan's atmosphere grows thick enough that clouds can form. They are not clouds of water vapor like Earth's gentle billows. These are clouds of organic compounds, methane, ethane, cyanoacetylene, other complex molecules whose names sound like poetry. The probe's instruments sensed them, measured them, began to sketch a picture of Titan's meteorology. Somewhere in that descending mist, the first Earth machines were beginning to encounter chemistry that is not chemistry as we normally think of it. It is as if we were descending not through an atmosphere, but through a different periodic table. The altitude numbers on Huygens's display climbed backward, counting down to 0. 3 kilometers, 2 kilometers, 1 kilometer. The surface was coming. And then, after that long descent through amber atmosphere, after the parachute systems had performed their invisible dance and the instruments had steadied themselves, the Huygens probe touched down. Not with drama, not with a crash or a bounce. It simply settled. The landing site lay in a region called Xanadu, a sprawling highland on Titan's equator, and as the probe's instruments began their first real conversation with this distant world, something remarkable and utterly tranquil became clear. The ground beneath the probe was not the hard, crater-scored regolith of the Moon or Mars. Instead, Huygens had come to rest on something far more familiar in its character, far more welcoming in its strangeness. The sensors detected a surface that was damp, clay-like, soft enough that the probe's feet had sunk slightly into it, as if Titan itself were settling the visitor into place with the gentleness of a hand. The soil composition, a mixture of water ice, perhaps granules of methane-soaked sediment, held a consistency more akin to wet earth than to frozen stone. Can you imagine that texture? A shoreline world where the grains are older than continents, where moisture means not water but the slow accumulation of liquid hydrocarbons, and yet the fundamental property remains. This was ground that could be touched, that could yield, that could hold the weight of an object from another world and cradle it softly. As the minutes unfolded after impact, the methane haze that had obscured everything during the descent began its own gentle settling. The wind, which had pushed and guided the parachute in its final stages, began to calm. The instruments recorded a transformation of atmosphere around the probe, the particulate matter drifting downward like snow, the air becoming clearer, though never truly transparent. What emerged in those first hours was something that perhaps only a handful of human minds had ever truly anticipated, an alien landscape that was not hostile or bizarre or chaotic, but rather quiet. Extraordinarily quiet. Titan revealed itself as a place of profound stillness. The images transmitted back to Earth showed something that struck observers with an unexpected melancholy. The horizon rose slightly, as it does on any world, but it was softened, hazed, drawn in shades of amber and brown. The immediate surroundings of the probe appeared rocky, but again, these were not the sharp, jagged formations of a crater rim or a high mountain pass. They were rounded. They had the appearance of stones smoothed by patient processes, perhaps the slow weathering of Titan's thin winds, perhaps the movement of organic-rich liquids across millennia, perhaps the freeze-thaw cycling of a methane climate over millions of years. The texture was almost gentle, as if the landscape had been worn into a state of acceptance, where hard edges had become soft thresholds, and everything that could catch or cut had been slowly transformed into something safe. The most profound impression was one of isolation, yes, but not hostility. Think of it this way. You have entered a beach, but a beach no human shore has ever known. The sand beneath your instruments is not silicon and feldspar, but hydrocarbons and ice grains. The air you are sampling is not nitrogen and oxygen, but primarily nitrogen, so thick that you feel its weight, mixed with methane and traces of other organics. The sea, if you could walk 300 meters or perhaps further, would be not water, but lakes of liquid methane and ethane, their surfaces barely rippling, their shorelines barely distinguishable from the damp surface around you. And yet the feeling conveyed by those first images, that first data stream, was almost one of arrival at a sacred place. A sanctuary, a world that had waited in its own patient silence for billions of years, and which had finally received a visitor who meant it no harm and asked only to witness and understand. The thermal sensors told another story of quietude. The temperature at the surface hovered around -179 degrees Celsius. In the depths of winter on Antarctica, or in the heart of deep space, one might find warmth by comparison. And yet at this temperature, substances behave with a slowness that rivals the patience of continental drift on Earth. Chemical reactions proceed at glacial pace. Processes that take seconds in a warm terrestrial laboratory might consume weeks or months in Titan's embrace. The world operates on a tempo that is fundamentally different from anything in human experience. Not dead, but profoundly, achingly slow. And in that slowness, there is a kind of deep rest, a kind of cosmic meditation. Xanadu itself remains something of an enigma. The name, drawn from Coleridge's poem, speaks to the unknowable and the wondrous. The actual region turned out to be less mountainous than pre-Huygens models had suggested, though it was higher in elevation than much of Titan's surface. It was a place where the probe could have landed and found outcrops, could have discovered a crossroads of sorts, a region where various processes and landscapes seemed to converge. The touchdown location specifically proved to be near the edge of a fluid-carved depression, a place where methane perhaps sometimes flows, or flowed, in ancient seasons now long past. The sensors detected a surface that had been shaped, over time, by these subtle movements of liquid, by the patient sculpting of winds measured in meters per second, by the slow, inevitable gravity of a world 1,500 kilometers across, but only 1/20th the mass of Earth. What strikes us, perhaps, most deeply about those final moments before silence and stillness became absolute, is how ordinary, how calm, how almost homely the sensation was. A spacecraft from humanity's world had touched another world. It had not found monsters or chasms or tempests. It had found, instead, a place that seemed to welcome contemplation, a place where the haze never fully clears, but also never overwhelms, where moisture exists, but not as we know it, where ice is bedrock, and organic compounds are the slow poetry of chemistry, written across landscapes over eons. Xanadu, in those first moments, was a beach that had never known a footprint, a shore where no waves crashed with violence, where the tide moved in slow cycles measured in seasons, and where, for the first time, Something made by intelligence had rested, and had listened, and had told us what it heard. And yet there is something profoundly soothing about the world that Huygens revealed, not through any single dramatic discovery, but through the patient accumulation of small, amber-tinted truths. For what began to emerge from that first clear image was a vision of a world wrapped in one of the thickest atmospheres known to any world in our solar system. Titan's nitrogen envelope is so dense, so layered and intricate, that it has fundamentally reshaped how we understand the light that falls upon that distant moon. Imagine standing on a mountain on Earth during a particular kind of winter twilight, that hushed moment just before dawn or just after sunset, when the sun hovers somewhere beyond the horizon, but its light still reaches you through the thicker portions of the air. The sky holds a faint, diffuse glow. It is neither night nor day. You cannot see the sun directly, but you are not in complete darkness either. You exist in a threshold, a liminal space, where illumination comes not from a point source above, but from all directions at once. This, in many ways, is the eternal condition on Titan's surface. The atmosphere there is so thick, nearly 1.5 times as dense as Earth's air at sea level, that sunlight arriving from across the solar system does not penetrate to the ground in the direct, sharp way it does here. Instead, it enters the upper reaches of that nitrogen ocean, and immediately begins its slow dance with the countless suspended particles floating there. Those particles are remarkable in their own right. There are crystals of organic ice. There are aerosol particles, complex hydrocarbons and other molecules that have been created in the upper atmosphere by the patient chemistry that occurs when solar ultraviolet light and cosmic rays strike methane and nitrogen molecules, breaking them apart and encouraging them to reassemble into longer, more intricate chains. These particles scatter light in all directions, in a process that physicists call diffuse scattering. Every photon of sunlight becomes subject to collision, to deflection, to the gentle nudging that these suspended particles provide. The result is a softening, a diffusion. The harsh point of light that is the sun, so distant, so small from Titan's vantage point, becomes transformed into a pervasive amber glow that seems to emanate from everywhere and nowhere in particular. Have you ever noticed how, on a heavily overcast day, there are no shadows, because the clouds have scattered the sunlight so thoroughly that it reaches you from all directions at once, and thus there is nothing casting a shadow in any meaningful sense? Titan lives, in a way, in a kind of perpetual soft overcast. But where Earth's clouds are made largely of water, Titan's haze is an organic kingdom unto itself, a vast suspended library of molecules that have been created over billions of years through the slow chemistry of that nitrogen sky. The color that results from this scattering is perhaps the most visually distinctive feature of Titan as viewed from spacecraft. It is not the brown or grey that one might expect from a moon shrouded in atmosphere. It is an amber, a golden amber, a russet-tinted twilight that speaks of complexity, of depth, of layers upon layers of chemical interaction. This is the color one sees in the photographs returned by Cassini, in the images captured by Huygens during its long descent, a warm, honeyed tone that seems almost to glow from within the moon itself, though in truth it is simply the interaction of distant sunlight with that profound atmospheric depth. And what is perhaps most soothing about this state of affairs is that it is, in a real sense, permanent. The sun never rises sharply on Titan. It never sets sharply either. There is no dawn that suddenly floods the landscape with light. There is no dusk in which shadows lengthen and the sky shifts through shades of purple and blue. Instead, there is an endless amber twilight, a soft, consistent, unchanging illumination that persists whether the part of Titan facing the sun is in the position we would call day or the position we would call night. The light that reaches the surface remains diffuse, gentle, filtered through hundreds of kilometers of haze, scattered by untold billions of suspended particles. The question of whether an observer standing on Titan's surface would experience any diurnal variation at all, any change in brightness from what we call day to what we call night, has occupied planetary scientists for decades, and the answer appears to be very little. The atmosphere is so effective at scattering light in all directions that even when Titan has rotated to a position where it presents its lit face toward the sun, and has also rotated again to present its dark face, the difference in illumination is subtle. One might describe it as moving from a slightly warmer amber to a slightly cooler amber, from a twilight that is a touch brighter to a twilight that is a touch dimmer. But the quality of light, that soft, all-pervading, diffuse amber glow, remains constant. This is not true of other worlds. On Earth, the contrast between noon and midnight is profound. The brightness of full daylight, with the sun high overhead and creating sharp shadows, is perhaps 10,000 times brighter than the light of a moonlit night. On Mercury, the contrast is even more extreme. The stark light of the sun, magnified by Mercury's proximity to the sun itself, floods the day side, while the night side descends into absolute blackness. But on Titan, the contrast between day and night is, in some measures, as small as a factor of 2 or 3. The atmosphere has engineered a kind of cosmic democracy of light, where all times of the Titan rotation are blessed with a similar, constant, gentle illumination. And there is something deeply restful about contemplating this. The idea that somewhere in the solar system exists a world where the light never changes drastically, where there is no blinding noon followed by desperate night, where instead there is simply an endless, patient amber twilight that pervades every moment of every Titan day, a period that incidentally lasts nearly 16 Earth days, given that Titan is tidally locked to Saturn and rotates in synchronization with its orbital motion. The haze itself is perpetually cold. Temperatures in the upper atmosphere hover around -180 degrees Celsius, cold enough that the organic particles and ice crystals suspended there are locked in a kind of frozen suspension. They drift slowly, buffeted by winds that, though present, are themselves gentle by comparison to the tumultuous winds of Jupiter or the storms of Earth. These winds shape the haze, carve patterns in it, create layers and gradients, but they do so in a way that is almost meditative in its slowness. When Cassini's instruments examined Titan's atmosphere in detail across its 13 years of orbit, they found evidence of these layers. There are distinct strata of differing chemical composition, differing temperatures, differing densities of suspended particles. Some of these layers vary with the seasons, and Titan, remember, experiences seasons that last more than 7 Earth years each. Others remain relatively constant. Together, they create a kind of laminated shield, each layer contributing its own mote of scattering, its own subtle deflection of light. What emerges from this understanding is perhaps one of the most profound relaxations that planetary science can offer. It is the realization that somewhere far away from Earth, orbiting Saturn in patient silence, exists a world where light has been so thoroughly transformed by distance and by atmosphere that it has become something entirely new, something that exists in a state of perpetual calm illumination, never harsh, never absolute, never extreme. A world of eternal, gentle, amber twilight, where the concept of day and night has been softened into something almost abstract, something that exists more as a mathematical definition than as a perceptual reality. And in that awareness lies a kind of peace. The universe, for all its violence and vast energies, contains within it pockets of profound stillness, moments and places where the fierce light of a distant star has been gentled and filtered and scattered into something so soft, so constant, so endlessly patient, that it seems to speak to some deep need within us for illumination that does not demand, that does not shift, that simply exists, unchanging, forever. And so we drift downward through those orange layers, past the amber twilight and the endless haze, until we reach something that might surprise you about this distant moon so very far from the sun. Beneath the thick nitrogen clouds, across the poles where the cold runs deepest, there exists something that moves, something that flows, something that mirrors a process you know intimately from your own world, yet transformed into a form almost unrecognizable. Titan holds seas. Not of water, but of liquid methane and ethane, great pooling bodies of hydrocarbon that lap against shores of dark material, in a rhythm as ancient and patient as any tide. When the Cassini spacecraft first peered through that orange veil with its radar instruments, cutting through the haze that had hidden Titan's surface from visible light, the images revealed something almost dreamlike. A patchwork of dark regions concentrated near the polar regions, some covering areas larger than Earth's own Great Lakes, others stretching across territories vaster than our Mediterranean. These were not mirages or shadows. These were reservoirs of liquid, real and measurable, existing at temperatures where water would be harder than granite, where the very concept of ice transforms into something like bedrock. Imagine, for a moment, a lake that never freezes, that never warms, that exists in a perpetual, tranquil state of coldness. The largest of these seas, called Kraken Mare, sprawls across an area comparable to Earth's Caspian Sea, a body of liquid that has been there for billions of years, perhaps since Titan's formation itself. When you think of the word sea, your mind draws up images of salt water, of blue-green horizons, of waves and motion, and the tang of brine. But on Titan, sea means something quieter. It means a dark, mirror-smooth expanse of methane and ethane, warmed slightly by the faint trickle of heat from Titan's distant sun and the internal warmth still radiating from within the moon itself. These are not violent waters. The surface tension of liquid methane at Titan's temperature is nearly 3 times greater than water at Earth's freezing point, which means any ripple that forms carries a particular weight and slowness to it. What draws the listener's attention most carefully is this. Titan possesses a complete, functional hydrological cycle, the very circulation of matter that makes Earth habitable and alive, yet executed entirely in a different medium. Where Earth's water evaporates from oceans and falls as rain, Titan's methane rises as vapor from these polar seas, drifts through the atmosphere as a trace component of that thick nitrogen blanket, travels across the moon's face, and descends again in the form of gentle methane rain. It is not constant. The rain falls in intermittent bursts, leaving behind temporary streaks of moisture on the dark surface. But it falls, it collects, it pools once more. The shorelines of these methane seas are a study in quiet desolation. Cassini's radar glimpsed the boundaries where liquid meets the darker terrain, and what emerges is a picture of remarkable geological stability. The shores are not jagged or turbulent. They lack the crashing waves of Earth's coasts, because the physics at those temperatures, under that pressure, create something gentler. The methane moves with a viscosity that Earth's water does not possess, thicker and slower, more deliberate. If you could stand, hypothetically, impossibly, at the edge of Kraken Mare and watch the surface, you would see no whitecaps, no spray. You would see stillness. You would see the faintest of ripples propagating across that smooth surface with an almost meditative slowness. The shores themselves are thought to be composed of water ice, hard and ancient as stone, perhaps mixed with organic material, that dark hydrocarbon-rich gunk that accumulates wherever complex chemistry occurs under Titan's strange conditions. Where the methane meets ice, the boundary is remarkably clean in some places, suggesting a delicate balance between geology and liquid, between solid and fluid, between the timeless and the slowly changing. In other regions, the boundary blurs. Complex networks of channels and branching patterns spread inland from the larger seas, dry now most of the time, but bearing the unmistakable signature of having carried liquid in the past. These are Titan's rivers. They are not always flowing, these waterways of hydrocarbon, but they have flowed. The evidence is written in the landscape. Do you know what might sound almost gentle about this? The extreme slowness of it all. The methane cycle on Titan unfolds on timescales that human observation can barely perceive. A rain shower might not come to a particular latitude for years. When liquid does flow, it moves deliberately, constrained by the physics of cold and dense atmosphere. There are no floods in the way Earth knows them, no torrential releases that reshape the landscape in days or weeks. Instead, there is a slow, patient carving. There is the long conversation between liquid and land, measured in millions of years, whispered rather than shouted. Within these methane seas and lakes, certain regions have been mapped with particular care. Ligeia Mare, the second largest sea, covers an area somewhat smaller than the North American Great Lakes, but with depths that remain largely mysterious. The Cassini radar could probe the surface, but the true depths of these hydrocarbon reservoirs are still unknown, hidden beneath the liquid itself. When you think of mystery on an alien world, you might imagine exotic creatures or hidden civilizations, but the mystery here is simpler and more profound. What lies at the bottom of these seas? What chemistry occurs in the depths, where methane and ethane press down upon whatever substrate lies below? The Cassini spacecraft detected the presence of waves on at least one occasion. A ripple pattern on the surface of Ligeia Mare, the gentlest undulation recorded by human instruments from across the vast gulf of space. The very existence of these seas transforms the way we understand Titan. It is not merely a static, frozen world, locked in geological stasis. It is a place where material moves, where cycles operate, where the flow of matter from one state to another continues in darkness and cold. Yet there is something profoundly restful about the scale and speed of it all. There are no human timescales here. There is no rush. The methane will pool and evaporate and rain and pool again. A rhythm older than mountains, older than continents. A slow breath taken by an entire world across the span of epochs. Across the vast equatorial belts of Titan, where the methane haze thins just enough to reveal the surface below, lie great expanses of dunes that stretch across thousands of kilometers in slow, orderly waves. These are not dunes of silica like those in Earth's deserts, sculpted by dry wind over millennia. Instead, they are dunes of hydrocarbon sand, grains of organic material so fine, so delicately assembled, that they seem almost like dust, composed of frozen possibility itself. When Cassini's instruments finally pierced the orange veil and mapped these regions with synthetic aperture radar, astronomers found themselves gazing upon something genuinely alien and yet oddly familiar in its patterns. Long parallel ridges running broadly east to west, sometimes separated by gaps of darker material, sometimes merging into one another in a hypnotic rhythm that speaks of wind, of time, of the slow movement of material across an alien world. The winds that shape these dunes are gentle by terrestrial standards. Titan's thick nitrogen atmosphere, though dense enough to produce weather and fill valleys with flowing liquid, moves with a kind of lethargy compared to Earth's tempestuous winds. A breeze that would barely ruffle your hair on Earth can, over sufficient time, move grains across Titan's surface with inexorable patience. And time is something Titan possesses in abundance. The dunes are not rearranged in seasons or even in human lifetimes, but across the vast, slow cycles of the Saturnian year. A single orbit of Saturn takes approximately 29 Earth years, and Cassini's observations spanned only 13 of those years, a mere blink in the history of Titan's surface. What may have appeared stable in those images might be, in reality, in the midst of profound but glacially slow transformation. Consider, if you will, the seasons on Titan. Earth experiences its seasons as 4 distinct, relatively equal periods, each lasting roughly 3 months, with marked transitions between them. The seasons are noticeable, insistent, easy to feel and observe. But Titan's seasons unfold across timescales that dwarf human experience. Each of Titan's 4 seasons lasts approximately 7.5 Earth years. A single winter on Titan is longer than a human childhood. Spring stretches across a span of time roughly equal to a doctoral degree program. A full seasonal cycle encompasses more than a generation. And in those slow seasons, the atmospheric circulation patterns shift, the winds change their character, and the great dunes respond with movements so gradual that no human will ever see them happen. No telescope will ever capture the change. No camera will record the transformation from one moment to the next. Yet the change is there, unfolding in the patient arithmetic of planetary mechanics. The dunes themselves tell a story about wind direction. Their orientation suggests that the dominant winds that shaped them, or perhaps continue to shape them, in that immeasurably slow way, come from a particular direction, driven by atmospheric circulation cells that sweep across Titan's equator. Models of Titan's circulation, developed by atmospheric scientists, propose that during different seasons, these wind patterns shift, sometimes reversing their direction entirely. When the wind reverses, the dunes do not instantly reform. Instead, new sand grains begin their slow journey in a new direction, gradually building new ridges, gradually erasing the old patterns, creating a palimpsest of wind history written in hydrocarbon sand. How many seasons worth of wind patterns might be encoded in a single dune formation? How many layers of meteorological history might lie compressed in those frozen waves of organic material? The composition of these dune grains themselves raises a gentle question that scientists have pondered with growing fascination. The grains are believed to be composed of complex organic molecules, tholins and other polymers that have been rained down from Titan's upper atmosphere, where ultraviolet light and cosmic radiation transform simpler hydrocarbons into more intricate structures. Over geological time, these particles settle, accumulate, and collect in certain regions, where winds have concentrated them into these great dune fields. So each grain in each dune represents a kind of captured chemical history, a fragment of Titan's organic chemistry, made tangible and mobile. The dunes are, in a sense, archives of atmospheric chemistry written in sand, waiting for some future explorer to examine them more closely and read the stories they contain. There is a peculiar stillness to these dune fields, a quality that comes through even in radar imagery and photographs transmitted across billions of kilometers. Perhaps it is the knowledge that the dunes move so slowly that no eye has ever witnessed their transformation. Perhaps it is the recognition that these patterns will persist, in recognizable form, for longer than nations rise and fall on Earth. Or perhaps it is simply the truth that under Titan's perpetual amber twilight, with its methane rain falling in brief intervals and its winds sighing in slow rhythms, nothing is rushed, nothing is urgent. Everything unfolds according to timescales that make even geological processes seem hurried by comparison. And there, in the spaces between the dunes, lies material of a different character, darker regions, sometimes interpreted as older surfaces or as areas where different winds have created different arrangements. The transitions between dune fields and interdune plains, between areas of active sand transport and areas of apparent stability, create a landscape of remarkable variety for a world that most of us imagine as a monotonous, featureless sphere hidden beneath perpetual haze. The reality is far more textured, far more subtly varied, a world of slow geological poetry, where even the sand writes verses that take 7-year seasons to complete. And yet beneath all that orange haze, below the winds and the methane rain, scientists believe something far more profound sleeps in the darkness, something warm, something liquid, something that might, in the quietest way, reshape how we think about water in the solar system. The evidence arrived slowly, gathered across decades of observation and calculation. Cassini's careful measurements of Titan's gravitational field revealed a subtle truth. The moon's interior does not behave the way a rigid, fully frozen world should. The density, the wobble in its orbital motion, the way its icy crust responds to Saturn's enormous gravitational pull, these whispered clues all pointed toward the same patient conclusion. Beneath that hard, frozen shell of water ice perhaps 60 to 80 kilometers thick, there exists what scientists now call a subsurface ocean, a global sea of liquid water, kept from freezing by the slow heat rising from Titan's rocky interior, and perhaps by dissolved salts that lower the freezing point, much as salt lowers the freezing point of ice on Earth's winter roads. Imagine that, a world within a world, an ocean no sunlight has ever touched, cradled between the cold hardness of ice above and stone below. We do not yet know the ocean's depth with certainty, and here the speculation begins to whisper its necessary uncertainties. Models suggest it could stretch anywhere from 50 to several hundred kilometers down, a layer of water so vast that it might contain more liquid than all the oceans of Earth combined, more water than humanity has ever known. But all of this remains inference, educated guessing built on the solid foundation of what the instruments measured but could not see directly. This is the honest boundary between what we know and what we believe we know, and it matters to hold that line with care. What captivates many researchers, however, is not merely that the ocean exists, but what might be happening within it. The heat rising from Titan's interior creates something remarkable, the possibility of hydrothermal chemistry. On Earth, where the ocean floor meets superheated rock near volcanic vents, water dissolves minerals and creates exotic chemical environments where simple life once emerged. Could the same ancient chemistry be occurring now, in the darkness of Titan's hidden sea, in the warm gaps where water touches hot stone? This too remains speculation, clearly so. But it is the kind of speculation that does not dismiss the possibility gently. It sits with it, it considers it. The subsurface ocean also creates a second implication, one that draws the breath inward. If water exists in liquid form within Titan, and if that water contains organic molecules, compounds of carbon and hydrogen that drift down through the methane rain or form in the lakes and seas above, then Titan's hidden ocean might be, in the most tentative sense, a place where chemistry could become extraordinarily complex. Not life necessarily, perhaps never life, but the slow building of molecular diversity, the kind of prebiotic complexity that might, under the right circumstances and across vast stretches of time, create conditions we associate with the emergence of something more. The speculation ends there. The science remains open. There is something profoundly moving about this image. A moon circling Saturn, orange and shrouded, its surface scarred by dunes and cratered by impacts, its atmosphere thick and impenetrable. And all the while, far below, a hidden ocean turning slowly in its own rhythm, its own chemistry, its own unfathomable patience. Heat from within, water enclosed, darkness complete. For billions of years, this ocean may have been there, and no one from Earth knew, no one saw it, And it continued, nonetheless, in its slow dance with the cold stone ceiling above it and the rocky warmth below. The instruments aboard Cassini could not penetrate that ice to touch the water directly. Voyager could not see through the haze to suspect it. Even now, we infer its presence rather than prove it absolutely. Yet this inference rests on mathematics, on measurements of mass and motion, on the laws of physics that apply just as surely on Titan as they do here. In that gap between certainty and possibility lies the frontier of planetary science, where educated speculation becomes the most honest answer we can offer. The subsurface ocean of Titan remains, for now, a place that teaches us humility. We can deduce its presence, we can imagine its character, but to truly know it, to measure it, to understand what happens in those depths, that awaits a future exploration, a future messenger, sent down through the ice to touch the darkness and report what lies there. And yet, beneath all this patient observation, the lakes, the dunes, the slow turning of seasons, there exists a question that draws the imagination inward, towards something far more subtle and perhaps far more profound than geography alone. What if Titan's thick, hazy atmosphere is not merely scenery, but a vast chemical engine? What if, suspended in that orange veil and dissolving in those methane seas, there are the very building blocks of something not quite alive, but undeniably alive adjacent? This is where Titan begins to whisper something almost philosophical to those patient enough to listen. The haze that softens Titan's features, that gives it its amber glow, is not simple nitrogen fog. Mixed within it, layered, complex, and endlessly generative, are molecules that form when ultraviolet light from the distant sun strikes the upper atmosphere. Solar radiation and cosmic rays break apart methane and nitrogen, scattering their atoms like puzzle pieces. Those pieces recombine, often in startling ways. They form larger, stickier molecules. Ethane emerges, acetylene, propane, and from these, over time and through countless collisions, something far more intricate begins to take shape. These molecules, many of them, bond together into larger frameworks. Scientists call them tholins. The word itself, derived from the Greek for muddy, carries a sense of organic mess, of complexity building from simplicity, layer upon layer. Picture this process not as a violent reaction, but as something far gentler. Imagine tiny particles forming high in Titan's thin upper reaches, where the radiation is strongest. These particles accumulate, they grow, they descend, and as they drift downward through miles and miles of atmosphere, a journey that might take weeks or months or years, they continue to interact with one another, bumping together, adhering, building larger and more baroque structures. By the time they reach the lower atmosphere, these organic aerosols have become substantial enough that they scatter light themselves, contributing to Titan's perpetual orange haze. It is, in a sense, a slow chemical snow, falling not as frozen water, but as microscopic flakes of prebiotic complexity. What makes this process so quiet, so patient, so worthy of sustained contemplation? Perhaps it is the sheer deliberation of it. In Earth's atmosphere, similar processes occur, but compressed, energetic, subject to weather and turbulence. On Titan, with its thicker air and slower winds, with its vast cold and its stable chemistry, this organic rain falls with a kind of inevitability. Year after year, season after season, the tholins accumulate not just in the atmosphere, but they settle onto the surface. They drift into the lakes and seas of methane and ethane. There, in those liquid hydrocarbon oceans, they undergo further transformations. Within the methane lakes, those strange, still bodies of liquid that mirror Earth's own oceans but in a fundamentally alien way, these organic compounds become soluble. They dissolve. they dissociate. They recombine. The cold, the pressure, the sheer time available in such a stable environment means that chemistry unfolds at a pace utterly unlike anything we experience on Earth. In those quiet methane seas, molecules may linger for millennia, slowly reacting, building towards something that is perhaps the frontier of speculation, where science respectfully pauses. Here, it is important to note, and to hold this thought gently, that we do not know if life exists on Titan. We do not have evidence of it. But what we do know, what observations and models increasingly reveal, is that Titan's surface and near-surface environment contains an astonishingly rich chemistry of carbon-based compounds. It contains energy sources, both from above, sunlight converted to chemical potential by those photochemical reactions, and potentially from within, through geological warmth or tidal friction. It contains solvent systems, both liquid methane on the surface and possibly liquid water beneath the crust. And it contains time, billions of years of time. In the history of astrobiology, this collection of ingredients has come to seem almost significant. The organic molecules that rain down as tholins represent what chemists sometimes call prebiotic chemistry, the chemistry of life's potential, the slow assembly of complex carbon molecules that, in Earth's ancient past, eventually organized into self-replicating systems. Whether or not Titan ever crossed that threshold, whether the molecules in its lakes have ever organized into anything we would recognize as living, remains unknown. But the simple fact that such chemistry is occurring, reliably, continuously, in the cold darkness of a world so far from the sun, speaks to something humbling about the universe. The cosmos seems profoundly inclined toward complexity. Given time, energy, and the right chemical palette, elaboration emerges. Not inevitably, perhaps, but naturally. Consider this. On Earth, we have found that complex organic molecules form in the interstellar medium itself, in the dusty regions between stars, under conditions of cold and radiation not so different from Titan's own atmosphere. Meteorites that have fallen to Earth carry within them amino acids and other biological building blocks, formed in deep space. Titan, then, might be seen as a kind of portable laboratory, a world where the universe's tendency toward molecular complexity is on full display. Each Cassini image that revealed another lake, each spectral reading that confirmed another organic compound, was in a sense a small whisper from across the solar system, a reminder that we inhabit a universe far richer in its chemical possibilities than we once imagined. The tholins themselves, those complex aerosols, exist in a kind of perpetual conversation with Titan's environment. In the upper atmosphere, they form from energy. In the lower atmosphere, they drift and merge. At the surface, some settle onto ice and rock, accumulating over geological timescales, perhaps forming the kinds of chemical reservoirs that could sustain unusual biochemistries. Others drift into the methane lakes, where liquid chemistry continues the work begun high above. It is a cycle, not a cycle of water, as on Earth, but a cycle of complexity, of carbon finding ever more intricate ways to organize itself under cold, patient, absolutely silent conditions. And what calls to us, perhaps, in contemplating this? It is the sense that even in the strangest of places, in a world so cold that metals become as hard as stone, where rain falls from the sky in liquid hydrocarbons and ice is bedrock, the universe continues its quiet work of elaboration. Complexity builds itself, molecule by molecule, season by season, eon after eon. Titan does not shout about this. It simply continues, wrapped in its orange haze, letting the chemistry unfold in the darkness, as it has been unfolding, likely, for billions of years. And we, so far away, can only listen and wonder what whispers back through that ancient, patient chemistry. And there, In those first soft images from Xanadu's surface, Cassini had found not an ending, but a beginning. For the probe that had delivered Huygens to that distant shore would itself remain at Saturn for 13 more years, orbiting in a long, patient spiral through the Saturnian system, returning again and again to circle Titan with a quiet persistence that had no parallel in planetary exploration. 127 times it would approach that orange world, each pass a careful maneuver, each orbit a chance to know something new about the hidden planet wrapped in its haze. The rhythm of those passes became a slow heartbeat in the outer solar system. 4 years, 5 years into the mission, the cameras of Cassini had begun to gather together the scattered pieces of Titan's surface, stitching them into a vast map that revealed a world far more intricate than anyone had imagined from those first blurred Voyager images. The radar, that patient eye that could pierce through the methane haze where optical cameras failed, traced out the signatures of hills and plains, found the confirmation of those methane seas at the poles, watched as seasons shifted and new features emerged from beneath the shifting haze. Each pass took the spacecraft only so close, never too close, always leaving room for mystery, always preserving that sense of distance and wonder that had drawn humanity to Titan since the age of telescopes. There was something almost meditative in the rhythm of those 13 years. While the cameras recorded, while the radar slowly assembled its map, other instruments listened to Titan's radio emissions, measured the pull of its gravity, analyzed the thin wisps of complex molecules that drifted in its upper atmosphere. The work was not hurried. It could not be. The spacecraft moved at its own pace, bound by the orbital mechanics of the Saturn system, and there was a kind of harmony in that constraint. When Cassini had not enough fuel or angle to approach Titan closely, it turned instead to Saturn's other moons, to the rings, to the planet itself. And then, when the geometry aligned, it would wheel back toward that orange face and drink in more data, more images, more subtle revelations about the world below. Between those passes, something quiet happened in the minds of scientists who had followed Cassini's long exploration. Impatience gave way to something deeper, a kind of intimate familiarity with this distant moon. They had watched its dunes shift with the slow change of seasons. They had followed the evolution of that strange methane storm that erupted near the equator in 2010, a rare weather event that reminded them that beneath that patient haze, Titan was still a world in motion, still a place where things changed and moved and surprised those who studied it from afar. And they had seen, in those carefully mapped lakes and seas, the confirmation of something that had always seemed impossible, that another world, orbiting a planet nearly 1 billion miles from the Sun, could possess standing bodies of liquid, could have shores and currents, and the slow movement of water and methane. 13 years was not forever, of course. No spacecraft lasts forever, and Cassini had always been designed with an endpoint in view. As the 2010s deepened, as fuel reserves dwindled to a level where new orbital maneuvers became increasingly risky, the mission planners began to think about what the spacecraft's final chapters should look like. They could have simply let it drift at the edges of Saturn's system, a silent monument to the age of grand exploration, but they chose instead something more poignant, a final descent. The grand finale, they called it, and that descent began in November of 2016, when Cassini performed a maneuver that would place it on a collision course with Saturn itself. There was no haste in this final act. The spacecraft was instructed to thread a series of passes between the outer edge of Saturn's rings and the planet's uppermost atmosphere, a narrow passage that had never been traversed before. These orbits were the closest and the most delicate of Cassini's entire mission, 22 times circling Saturn in that impossibly narrow lane, each pass yielding data about the rings, about the planet's interior structure, about the storm systems that coiled beneath that golden atmosphere. And each time it emerged from that passage, Cassini still had work to do, still had instruments recording, still had stories to tell about the Saturnian system. It was on September 15th, 2017, after 14.5 years of exploration, after having mapped Titan's surface with a patience and care that had transformed that world from a fuzzy orange dot into a place with geography, weather, chemistry, that Cassini reached the end of its long journey. The spacecraft had been instructed to aim itself deliberately at Saturn's upper atmosphere, to burn up in a final dive into that golden haze, ensuring that it could never crash into and contaminate Titan or any of Saturn's moons that might someday harbor life. In its final moments, still falling, still transmitting, Cassini sent back measurements of the thin upper layers of Saturn's atmosphere. The signal grew fainter, fainter still, until there was only silence. And in that silence was the strange peace of a mission complete, a final descent made with intention, with the knowledge that every moment of that long, careful journey had been preparing for this last whisper into the cosmic dark. What had Cassini accomplished in those 13 years of quiet work? It had transformed Titan from something mysterious into something known, not fully known, never entirely explained, but known well enough to see the outlines of a world. It had shown that Titan was real in a way that mathematics and modeling could never quite capture. The mission had been an act of patience, a faith in the slow unfolding of understanding. And as the signal faded that September morning, as the spacecraft fell into its final silence, there remained behind an inheritance of images, data, questions, a quiet invitation for whatever explorers might come next, to continue the slow work of understanding this strange, hazy, endlessly fascinating moon. And yet the story of Titan does not conclude with Cassini's long farewell. Instead, it turns toward a future that has already begun to take shape in the laboratories and planning rooms of NASA and the European Space Agency, a future that promises a different kind of encounter with this distant world. There is a mission in the making, one that carries a name drawn from mythology and biology alike, Dragonfly, and it will arrive at Titan sometime in the early 2030s, perhaps in 2034, carrying with it a new vision of how we might move across an alien landscape. Unlike the orbiters and the single probe that descended to Xanadu before it, Dragonfly will fly. This is perhaps the most remarkable thing to contemplate about it. Rather than setting down in one place and gathering data from that fixed point, Dragonfly will be a rotorcraft, a kind of airship with multiple rotors, designed to lift off from one location and drift slowly across Titan's surface, sampling and studying as it moves through that thick nitrogen air. The atmosphere that once seemed so impenetrably shrouded to the astronomers of centuries past will become, in a way, a medium for exploration, a fluid space through which an aircraft can navigate with unhurried intention. The Dragonfly mission is built around a principle of patience and thoroughness. Its designers have imagined it not as a rover that must creep across terrain, but as something altogether different, a hopping explorer that might travel from dune field to dune field, from lake shore to ancient impact crater, moving at a pace that allows for genuine scientific investigation at each stop. Consider what this means. The dunes that Cassini glimpsed from above, those great curved ridges of hydrocarbon sand, sculpted by Titan's slow winds across millions of years, these will finally be examined, not from orbit, but from within their own landscape. A rotorcraft can settle near the crest of a dune and sample the texture of the surface, can measure the chemistry of the sand grains themselves, can record the whisper of wind moving across that otherworldly terrain. And then it can rise again, those rotors humming in that dense atmosphere, and travel onward. The distance it might cover is genuinely impressive when considered against the constraints of a battery-powered device operating at temperatures of nearly 180 degrees Celsius below freezing. Over the course of a mission lasting perhaps 2 to 3 years, Dragonfly could traverse tens or even hundreds of kilometers, moving from region to region with a kind of methodical grace. Each location will have been chosen with careful consideration, sites that speak to different questions about Titan's geology, its chemistry, its climate. There is talk of flying to the edge of Kraken Mare, the largest of Titan's northern seas, to examine the shorelines where liquid methane laps against solid ground. There is the possibility of visiting impact craters, where warm material from beneath Titan's icy crust may have been excavated and exposed, perhaps creating environments of greater chemical complexity. What might Dragonfly see and measure as it hovers low over these places? Imagine the rotorcraft descending toward a margin where Titan's hydrocarbon sea meets the land, the water vapor and methane rising subtly into the already saturated air. Its instruments will taste that interface, analyzing the chemical composition of spray and mist, seeking any evidence of how the liquid and solid surfaces interact, how they exchange molecules over time. On a dune field, the rotorcraft might conduct experiments in place, examining how the sand responds to the weak gravity and to Titan's sparse but persistent wind patterns. These are the kinds of quiet scientific moments that accumulate into understanding, not dramatic discoveries, but careful, systematic observations that gradually reveal the workings of an alien world. The engineers who designed Dragonfly have given considerable thought to how it will operate in Titan's peculiar environment. The atmosphere, though dense, is not so thick as to be impossible for flight. In fact, the combination of that thick air and Titan's low gravity, only about 1/7 of Earth's gravity, creates conditions that are almost gentler for flight than one might initially assume. A rotorcraft that would seem unwieldy in Earth's skies becomes something graceful here. The rotors can turn more slowly, can be larger and less mechanically stressed. There is a rhythm to operation on Titan that seems somehow fitting for a place defined by slowness and patience. Between flights, Dragonfly will land and settle into its own patient waiting. It will conduct measurements, gather samples, process the data it has collected. Its nuclear power source, a radioisotope thermoelectric generator, will sustain it through Titan's long nights. And Titan knows very long nights indeed, since it is so distant from the dim sun. The rotorcraft will maintain its instruments and prepare for the next leap, the next journey across that amber-hazed landscape. There is something deeply meditative about contemplating this future mission. We imagine Dragonfly rising from the ground near some unnamed dune or unnamed shore, the rotors lifting it into that perpetual orange twilight, the landscape slowly unfolding beneath its sensors as it climbs and moves. From above, Titan's terrain will reveal itself not all at once, but gradually, over many flights and many stops. The mission is designed not for speed but for depth, for a kind of intimate, methodical understanding of a world that has waited billions of years for a visitor. And perhaps that is the final gift that Titan offers to those of us who dream about distant worlds and patient science. It teaches us that exploration does not always need to rush. Sometimes the most profound understanding comes from slow, deliberate movement, from stopping to examine, from returning to familiar places to learn them more deeply. Dragonfly will carry this lesson into the 2030s and beyond, drifting across Titan's surface with the careful grace of something that has learned that there is no hurry when the cosmos itself has eternity. And so we return, in thought, to that amber world suspended in the outer dark, wrapped in its thick cloak of nitrogen and haze, turning slowly beneath the gaze of a distant, patient sun. Everything we have traced tonight, the orange veil that hides what lies beneath, the methane rivers that carve their quiet paths through highland and lowland, the hydrocarbon dunes that shift with each slow Titanian season. All of it speaks to a single, profound truth. Patience is woven into the very fabric of that distant moon, as fundamental to its nature as nitrogen is to its air. For more than 3.5 centuries, Titan has asked us to wait. It waited while Christian Huygens squinted through his imperfect lens, seeing only a speck of light. It waited through the long centuries that followed, while the brightest minds on Earth could barely guess at what lay hidden beneath its clouds. It waited through the space age itself, through decades of rockets and missions, until finally, only in our own modern moment, we began to glimpse its true face. And even now, with all that Cassini revealed, with all the data we have gathered and analyzed and slowly transformed into understanding, Titan remains fundamentally patient. It does not rush its revelations. Its seasons turn with ancient, measured grace. Its seas lap against their shores without haste. Its winds carry their burden of organic molecules downward through the haze at their own steady pace, molecule by molecule, building complexity in the depths of a cold, silent atmosphere. There is something deeply calming in contemplating such patience, is there not? In a universe that often feels frantically rapid, data streams, light-speed calculations, the dizzying pace of discovery in our own solar system alone, Titan invites us to slow down. It asks us to sit with mystery for a time, to accept that understanding unfolds not in moments of sudden brilliance, but in the accumulation of small, careful observations, in parachutes descending through fog, in radio signals traveling for over an hour to reach Earth, in the careful assembly of knowledge, piece by piece, year after year, decade after decade. When we think of Titan's haze now, we might think not merely of chemistry, the complex tholins and organic molecules drifting downward like a gentle snow, but as a metaphor for the nature of cosmic understanding itself. We cannot see through that haze directly. We must infer, we must imagine, we must build models and test them slowly against reality. And in doing so, we practice something ancient and necessary, the art of patient inquiry, the willingness to accept that some answers take time. Some truths require decades of waiting, of watching, of listening to the whisper of instruments and the patient accumulation of data. Beneath Titan's visible surface, we suspect, lies a global ocean. Liquid water, perhaps miles deep, circulating beneath an icy crust, kept warm by the slow decay of radioactive elements in Titan's rocky core. We cannot see it, we cannot yet touch it, but we know it is there, or we strongly suspect we do, through the patient work of gravity measurements and thermal models and the careful reasoning of planetary scientists who have spent their lives studying that distant world. Is that not itself a form of poetry? That we can know something exists, can understand something of its nature, can even ponder the possibility of chemistry within it, all without ever laying eyes upon it directly. That is the gift of patience in science. That is what Titan teaches. And as you drift now, somewhere in the darkness of your own room, on this distant blue world, imagine for a moment that slow ocean beneath Titan's frozen crust. Imagine its currents moving through cold water, carrying dissolved minerals and simple organic compounds. Imagine the pressure, the darkness, the profound quiet of that hidden realm. There is something soothing in the thought of such hidden depths, is there not? Of worlds within worlds, of mysteries that wait patiently for the day, perhaps years from now, perhaps decades, when humanity will finally send another visitor to Titan's surface. Dragonfly will come, moving slowly on electric rotors above those hydrocarbon dunes, and it too will teach us patience, showing us one small piece of Titan's landscape at a time, refusing to rush its careful cataloguing of that alien shore. Titan reminds us that the universe is not in a hurry. Stars turn in their slow orbits. Galaxies drift through the void across billions of years. Moons circle their parent planets in rhythms that dwarf human lifespans entirely. And in learning to pace ourselves to the rhythm of such distant worlds, we find something valuable. We find a kind of rest, a gentle unclenching of the mind's grip on urgency, a soft invitation to slow down, to watch, to wait, to let understanding accumulate gently over time, like methane rain falling through an orange haze. So let Titan's silence settle around you now. Let its thick atmosphere drift softly through your mind. Let the image of those methane lakes, still and vast and ancient, ease you downward into that slow, patient darkness where all understanding begins. That distant moon will continue turning, will continue its slow cosmic waltz with Saturn, will continue wrapping itself in mystery and patience, whether we are watching or not. And in that constancy, in that unflinching commitment to its own quiet rhythms, perhaps we find a model for rest itself, for the gentle, patient, unhurried unfolding of peace.